used in a lot of the thermodynamic programs you see today. Before we go too much further, we should probably talk a little bit about the major components of a practical refrigeration system. First, on the bottom, the evaporator. This is typically just copper tubes or aluminum tubes with copper or aluminum fins to help transfer heat. Its sole purpose is to let the refrigerant boil at a certain pressure. Then air is blown across the fins to cool the product and condition the room or whatever the purpose is for the system. Now, if you had an infinite amount of liquid refrigerant in a huge cylinder that was free and was okay for the environment, you could just run it through the evaporator at the correct pressure, let it go out, and you wouldn't need anything else. You'd be refrigerated. Kind of like the propane tank when you're cooking. That pressure is being released, it gets cold. If you open that propane tank and wanted to cool a room, don't do this, it would cool the room as long as you had refrigerant in there. But you got to have some way to turn that gas that escaped back into the liquid so that you can boil it again and again and again. The bulk of this webinar is just going to show how it is that we can have a continuous cycle of boiling the refrigerant and bringing it back to a liquid and boiling it again. A quick note here that going forward in this webinar, I'll be using water as an example of refrigerant. Water is a molecule just like any refrigerant. It's just that it boils at a higher temperature compared to typical refrigerants we use, and so we don't really use water for refrigerant here. I do this because we tend to think refrigeration processes are somehow confusing. By using water, which is intuitive to us, we will be able to see refrigeration as simply the boiling and condensing of a substance. So anyway, two other important concepts in refrigeration are sensible and latent heat. Sensible heat can be described as heat that increases the temperature of the substance. You can think of it as making sense, since adding heat intuitively should increase the temperature of the substance, like water. Latent heat is heat that does not change the temperature of the substance. This occurs during a phase change. This can be the change from a solid to a liquid, like liquid water to ice, or reverse, liquid to solid, or from liquid to gas, like boiling water, or of course, the reverse, gas to liquid. Looking at the diagram, we see the sensible and latent heat for water. Temperature, as you see, is on the vertical axis. Increased heat is on the horizontal axis. Let's start at the lower portion of the graph. The water is very cold at below minus 40 degrees Fahrenheit. The water is obviously ice at this point. As we add heat, the ice stays in ice form, but it does increase in temperature. Once again, sensible heat. Once the water reaches 32 degrees Fahrenheit, as we all know, it starts to melt. As we continue to add heat, it continues to melt, but it does so at this constant 32 degrees Fahrenheit. Once again, this is latent heat. Once all the ice is melted, we once again get into the sensible heat range. The instant all the ice is melted and we continue to add heat, the liquid water will increase in temperature, as you can see in this slanted line. Once again, this is sensible heat. Adding heat, temperature's going up. Once we hit 212 degrees Fahrenheit, as we know, water will start to boil. And it's going to boil at a constant 212 degrees Fahrenheit as long as there's any liquid left. Once all the liquid is gone, the temperature begins to rise again. In refrigeration, you know this as superheat. As we'll see later, the area of the graph where the water boils, and then when it increases in temperature, once it is all boiled, is the same as what happens to refrigerant in an evaporator. This area where the temperature increases is called superheat, like I said, and the last slanted line in refrigeration terms. And the horizontal line there is in the evaporator where the refrigerant is boiling. For instance, if your home air conditioner is using the refrigerant R22, the evaporator will have liquid R22 boiling in the evaporator at about 45 degrees Fahrenheit. Of course, the pressure is not going to be atmospheric, 0 psig, like in this water example. But the R22 is doing the same thing as the water boiling at 212 degrees. It is boiling at a constant pressure and temperature. It's just that R22 has different characteristics and boils at a different temperature. In fact, at atmospheric pressure of 0 psig, R22 boils at minus 41 degrees Fahrenheit. This is why technicians have to be very careful when taking hoses off systems. That cold refrigerant can burn your fingers. In fact, one of our team members actually has no fingerprints because of all his years doing HVAC service. Now, the fact that a fluid will boil at a constant temperature in the latent heat zone is key to refrigeration. It allows us to have a constant temperature difference between the evaporator and what we're trying to cool. As we saw on the previous slide, a fluid, such as water, has a certain boiling point. What we didn't mention so much on that last slide was that water that was boiling at 212 degrees Fahrenheit was doing so at a specific pressure. In that case, it was atmospheric pressure, or 0 psig. The graph shown here gives the boiling point of water for different pressures other than 0 psig. As the pressure increases, the boiling temperature increases. This is one of the laws we talked about earlier. We're going to be using this graph in subsequent slides. This point along the red line, this point of a substance is called its saturation point. It's where you have a combination of liquid and gas. It's boiling or condensing. At every pressure, there is a specific temperature at which the substance will boil. A quick aside on what psig means. Psig refers to the pounds per square inch gauge. This is the pressure compared to atmospheric pressure. Atmospheric pressure is 0 at sea level. So a set of refrigeration gauges open to air pressure at sea level should read 0 psig. Okay, back to pressure and temperature of water. If you boil water in a pan on your stove, it's going to boil at 212 degrees Fahrenheit. We all know that. This is where those dashed lines are, 0 psig, 212 degrees Fahrenheit. But if you reduce the pressure at the red star down to, say, minus 12 psig, the boiling point is going to go down to about 135 degrees Fahrenheit. We're adjusting the boiling point by adjusting the pressure. On the flip side, if you raise the pressure with something like a pressure cooker, the boiling point is going to rise. Pressure cookers can raise the pressure to as high as 15 psig. At 15 psig, water boils at 250 degrees Fahrenheit. And this is one of the ideas behind a pressure cooker. You can cook at a higher temperature without boiling the water and drying out the food. I think you've all probably seen this on your stove when the water's boiling and you have the lid on it and you push down hard on the lid and the water stops boiling. You raise the pressure, you raise the boiling point. So basically, by adjusting the pressure, we adjust the boiling point. And as we saw on the previous slide, in a refrigeration system, the refrigerant also boils at a constant temperature in the evaporator. Just like adjusting water's boiling point, we can adjust a refrigerant's boiling point. This is how we adjust the cooling temperature of refrigeration system. This graph here is for R22, same as water, but it's the R22, the pressure temperature graph. So with refrigerant R22, we can keep food frozen by keeping the pressure at 10 psig, at the blue star. At 10 psig, the boiling temperature of R22 is minus 20. It's boiling at minus 20 in the evaporator, and we're blowing air across it to keep the food frozen. We can also do air conditioning with R22 by keeping the pressure at 75 psig, at which the refrigerant is going to boil at 44 degrees Fahrenheit in the air conditioning evaporator coil in your house. As I said earlier, since this is a fundamentals course, I want to depict an air conditioning